Now we will see transformer networks, which is a new kind of network of deep neural networks that has been used in particular for natural language processing. The idea behind transformer networks is to use some kind of attention mechanisms to establish the relationships between elements in a sequence. So for example, in NLP, we are dealing with text, with sentences, and with transformer networks, we are looking to establish the link between each word of sentences to get some meaning of this. And the idea of transformer networks has been developed with the capacity to be able to run, to make parallel processing with multiple heads, and in that way being able to make an efficient use of GPUs. So this is by design made to be efficient on GPU while being effective in terms of doing the processing it is aimed for. In a transformer network, we have an encoder component and a decoder component. Some versions has only one or the other, but in the basic transformer model, we have both of them. And we don't make use of recurrence, contrary to recurrent network. The attention mechanism is giving the ability to use the whole context. So there's no need to get, I would say, recurrence, not even need to get some memories. The attention will make the links between all elements of the sequence. So of course, the transformer network is dealing with the whole sequence and is able to processing it that way to be able to relate the different words in a given sequence as input and be able to figure out the context and the relation between the words or whatever the elements in the sequence. So transformer networks are it is a central model. So many transformer networks have been developed for, several of them have been developed for large language models. Just think about GPT. So GPT is the T of GPT is for transformer. BERT is the same. It's also one of the first most successful transformer model developed by Google. There's also a version of transformers that has been developed for dealing with images instead of text or sequences. More prominently, the vision transformers, VIT, which are useful tools for dealing with images, speech recognition, etc. So this is the I would say the diagram representing a transformer network, the original transformer model. It is made of, I will present it through 4 different parts. So the first part is the inputs. Here we have the input, and the input goes through some kind of lexical embedding, so that is used to transform the words into some kind of numerical values, over which we add some notion of positional encoding, so it allows to get, I would say, the position in the sentence, for example, or in the sequence of a given input. So this is building up some kind of vectorial representation of the sequence that we are dealing with. In fact, it will be a numerical representation for each element of the sequence, each word of a sentence, for example. And this is fed to the encoder. So the encoder is made of multi-head attention, which is an important component of transformer networks. So, and some renormalization, also a module here and a feed-forward, more fully connected network, and so on. So these are extra elements, but the key element here is the multi-head attention, which is calculating the attention between all elements. So we are kind of being able to compute the relation between each element of the sequence and use this to interpret, to analyze the content of that sequence or the meaning or what we want to achieve with it. And then we also have the output. In fact, the output is somehow what we want to produce as output. So if we just feed an input sequence, we will produce an output sequence, and we will process one element at a time here in the right part of the model here. So we have the output we have so far. So and we transform the current output that we have and up to the current point in the sequence into a vector. So each element of that sequence is transformed into some numerical representation. And then we have the decoder. So the decoder, the first step is only on the mask output. So basically we have the output so far and we are masking it. The relation is not complete. We are just looking at the relation between the elements we have at that point. And then we are combining the input and the output representation. So we have the output that is fed as one element of the multi-head attention, which receive as other elements what we add from the input. So we are kind of relating the output with the input. and then we do some processing here, and then we have the output probability. So it somehow give us the probability over the next element of the sequence, like the next word in our sentence that we'll produce as output. And then once we have produced or decided to pick one element here, we add it to the output as the input, and we go with the next element. So we kind of choose the element and then go to the next one in output, and we generate elements one by one through this process in that model. So the core element is the attention mechanism. So here we see the equation used for that. It's relatively simple. So we have the matrix Q, which is for the query, K is for the key, and V is for the value. So we have the attention over Q, key, and V, and which is put in that equation. So we have Q multiplied by K transpose divided by square root of dk. So the values Q, key, and V are in fact the results from the application of weights, WQ, WK, WV, over the data X. So this is the results of applying one layer of weights over the input of the attention over the data by itself somehow, when we are dealing with the input module, the input part. And the division by the square root of dk is to stabilize the gradient. So basically dk is the size of the key, K. So each head works in parallel. So we have many of these heads stacked. You know, if you look back at this model here, we see multi-head attention. We don't have only one. We have many of these head mechanisms that are working in parallel. We can have, I would say, dozens of them. So each of them are making a different analysis with different weights. So the weights here are different for each head. And so the attention is computed differently between the element of the sequence according to these different matrices. So it looks like this. So basically this is one head, and then we have like the input. So if we say just X as input, can be when we are mixing input and output, it can be mixed, but let's say we are dealing only with the input here. So we have X, which is passed through the weights that give us the Q, and which is given to the softmax function, likewise for the K, and the V is multiply point-wise. So element-wise, we are making the product between the result here of the softmax and V to get the output, which we call Z here. So this gives us this kind of result where we get, for example, just for one word, and we have it for different words. But I would say for the word it in that sequence, we have the association within the same sentence with the other words, which is like this. So we have a strong association with the and monkey and banana, a little less with itself and with that. So this is the relation that one attention mechanism can provide. And we have many of them with different results possible that are bringing up these different attentions to get the relation between the element of the sequence. So an example here where we apply the model to translation. So we have an English sentence and we want to translate it in French. So we have as input the English sentence, as output the French one, and we want to produce that French sentence, which is completed here. So basically we have as input the soup tasted like socks. So this is our input. We put it into the input with several transformer blocks that are transforming this input in some kind of representation. And then we have the output here where we just put one at a time. So let's suppose that we are not at the last word here, but we could have been earlier in the process, and then we go through this. So we have the same attention mechanism apply on the output so far, and then we compute the mask self-attention and the encoder-decoder attention, which is kind of two things. We are kind of looking first at what we have as output, and then we are mixing the output and the input to get some kind of representation, which is then transformed into some probability over the target. So what is the next token? What is the next word in a sentence here? This is what we've got. So we've got a choice between all these words to be one of those. Not would be one of those. It would be a probability over all the possible ones. So then we can pick the word, which may be either the most likely or just proportional to their probability. We pick one token as the next one. As large language models, we know BERT. So BERT is based on transformers. So it has been proposed in 2018 by a team of Google researchers. BERT stands for bidirectional encoder representations for transformers. It is consists of a lexical embedding module, several layers of self-attention encoders, and then conversion to probabilistic output. We don't have decoder. In BERT, we only have self-attentive encoders. It became, when it was released in 2018, in a matter of 1 year, it became super commonly used for different application in NLP. So it's really a milestone element for NLP. Since 2020, virtually all English search queries on Google are processed by BERT. Another one that is now super well known is GPT. So it's basically the OpenAI family of transformer-based models, which started in 2018 with GPT-1, and now GPT-3, which we heard of, is in fact GPT-1 with some modified normalization and big scaling. So we really go from something relatively small with GPT-1 to a huge model of 175 billion parameters trained on 500 billion tokens. So this is the GPT-3, and GPT-4 is even much bigger, but we don't really know what it is because OpenAI tends to be quite opaque right now. This is more closed than it was before, but it is estimated that it has 1.7 trillion parameters, which is huge. And ChatGPT is in fact the integration of GPT 3.5. So it's basically an updated version of GPT-3 or GPT-4, depending if you are paying for ChatGPT. And we are joining this with, this is the key of ChatGPT, reinforcement learning with human feedback. So this is the idea of using human feedback to better align the output of GPT in ChatGPT to what we expect, both in terms of the relevance and also to control it, because sometimes it tends to, if it is not controlled, GPT tends to reproduce bad kind of answers or behaviors. I would say somehow bad language. So we'll reinforcement learning with human feedback. We kind of realign it within the expectations and get really the chatbot to be able to provide the right type of answers that we expect from some queries. There are also the vision transformers, which is another model that is the adaptation of transformer architecture to computer vision. So instead of processing word sequences, we process fixed size, non-overlapping image patches. So really now the patches are some other words that we have in sentences. So we are using these patches, which are in fact 1D vectors of small 16 by 16, for example, or it can be some other dimension, but that's the typical patch size of 16 by 16, which is packed into a 1D vector, plus some positional information to help to figure out where this patch is in the image. So the patch representation is provided as a sequence to the transformer network. So we just process the patches in the some order, some regular order, to make the transformer to process it as if it was a sequence of small images. But we know that these small images are in fact building up a bigger image. And the point with VIT is that it is able to capture complex and even distant relationship between images without requiring convolution layers. So we are able with this attention mechanism to replace convolutions, which is quite helpful and interesting in terms of capturing local relation between elements in an image. And VIT is able to achieve state-of-the-art performance with sufficient data and resources. So it is quite good for that. It is quite efficient at generating state-of-the-art performance. So, but we need very large data sets. So compared to CNN, a convolutional neural network is more efficient in terms of data. It requires less data than a VIT, which is kind of really needy in terms of data sets, in terms of size of the data sets, and also quite intensive in terms of the processing power required to achieve good results. So this is the diagram of a vision transformer. So basically, if you look at it, it's very similar to the basic transformer we saw before, with the difference is that we are dealing with patches. So we have this kind of image, which is divided in patches, and each patch is provided to a linear projection where we are flattening it with where we add some position embedding, and then we give it to the transformer encoder, and it processes it in some ways and gives some output in terms of classification, for example. And the transformer encoder is pretty much the same that we had before with the basic transformer, but with the difference here that we have an MLP instead of a single layer to process after normalization.